So part C, or step 3, is analyzing the second derivative. That gives us the intervals of concave up and concave down, and also our inflection points. So let's remind ourselves again what our original function is and what the derivative was. So our original function f of x was the function x to the fourth minus 4x cubed plus 5, which told us that our derivative of the function was 4x cubed minus 12x squared. And that tells me now I can analyze the second derivative of the function. The derivative of 4x cubed is 4 times 3x squared, which is 12x squared. The derivative of negative 12x squared would be negative 12 times 2x, which is negative 24x. Again, we set this equal to 0 or undefined. It's never undefined because it's a polynomial. I look to factor it. I know I can factor out a 12x from it. 12x squared divided by 12x is just x. And negative 24x divided by 12x is a minus 2. So that factors into 12x times x minus 2. I set each of those factors equal to 0. 12x equals 0 gives me x equals 0. And then x minus 2 equals 0, adding 2 to both sides gives me x equals 2. Again, what are these? These are possible inflection points. They are not critical values. Critical values is the first derivative. These are possible inflection points. How do I find out if they are inflection points? Well, I need to look at that number line. Here's x equals 0 and here's x equals 2. Again, I'm looking at the sign of the second derivative here. The second derivative is 0 at both of those points. I consider the first interval, which is negative infinity to 0, the second one, which is 0 to 2, and the last interval, which is 2 to infinity. Again, I'm trying to find out what is the actual shape of my function f of x by testing a point in each one of those intervals into the second derivative. So what part of the second derivative do I want to plug it into? I'm going to plug it into the factored form, which was 12x times x minus 2. I need a number less than 0. How about negative 10? A number between 0 and 2? How about the number 1? And a number bigger than 2? How about the number 10? I plug those in and I check the sign of each of the factors when I plug each one of those numbers in. 12 times negative 10 is a negative number, and negative 10 minus 2 is a negative. A negative times a negative is a positive. Since that test point was positive, every point in that interval must be positive. I plug in a 1. 12 times 1 is positive. 1 minus 2 is negative. So that's positive times a negative, which is negative. So that entire interval must be negative because that test point was negative. I plug in a 10. 12 times 10 is positive. 10 minus 2 is positive. And a positive times a positive is a positive. Since that test point was positive, that entire interval must be positive. So now I go back to that number line and I look anywhere that my second derivative is positive. I know my function is concave up, or one part of a smiley face. Negative concave down, or some part of a frown. Again, positive concave up, some part of a smiley face. And I also note that I have 2 inflection points here. Again, an inflection point is where it is in the domain of the function. The original function is polynomial, so it's most definitely in its domain. And it has to change concavity, which it does from positive to negative or negative to positive at those points. So I need to actually find those points. Again, how do I find those points? Well, I need to plug them into the original function, that original function being x to the fourth minus 4x cubed plus 5. I need to plug in those two values. It was 0 and 2 were the two numbers that I'm plugging in. And again, that's going to tell me that 0, whatever the y value is an inflection point. And 2, whatever the y value is also an inflection point. Nice thing is I already have this typed into my calculator, the table feature. So I just have to hit 0 for x and I get 5. We already knew that. That was our y-intercept. I hit in 2 for x and I'm getting negative 11. So that tells me my 2 inflection points are the points 0, 5 and the points 2, negative 11. Concave up was any time where that second derivative was positive. That was on 2 intervals, the first interval being negative infinity to 0, the second interval being 2 to infinity. Concave down, that's any point in time where the second derivative was negative, and that was on the interval 0 to 2. So now I've analyzed the second derivative and gotten all the information I can, intervals of concave up, concave down, and inflection points. So what do I do at this point in time? I'm going to go through and mark anything that I know from any one of these parts. So parts A, B, and C, which is steps 1, 2, and 3, right? So part 1, step A, was pretty lame. It didn't give us any x-intercepts, but it was able to give us that y-intercept of the point 0, 5. Let's look at part 2, again, increasing, decreasing, max, and mins. Let's see what we could get from that. Well, from part 2, we definitely got that the point 1, 2, x equals 3. I'm just going to put down here, sure, why not? This is 3, negative 22. Again, my y-scale is not too accurate here. We know that that point is a minimum point. Let's look for any other points. We know that the point 0, 5 is an inflection point. So I'll just write IP next to it. And we also know the point 2, negative 11, which would be about right there, is also an inflection point. Okay? So what do I want to do now? Now I want to do the number lines from part B, or step 2, and the number lines from part C, or step 3, directly below this exact graph to scale. So go back and look at your number line from part B and copy it here. So the number line from part B was broken up at 0, sorry, let me use red here, was broken up at 0 and 3. Again, I'm going to draw this down quite a bit so I can put both of them in the same place. This is x equals 0 and x equals 3. I look at the sign of my first derivative. It was negative on the first interval, negative on the second interval, positive on the third interval. We knew that at x equals 3 was a minimum, and we already determined at x equals 0 it was a inflection point. Let's move on to our second derivative in the sign chart for the second derivative. That was broken up at 0, which we've already done, but now we do need to also break it up at x equals 2. That's a point that we care about. And at x equals 2, we know it's an inflection point as well. And we want to look at the second derivative, the sign of the second derivative on those. Okay, so anywhere before 0, the second derivative is positive. Anywhere between 0 and 2, the second derivative was negative. And anywhere after 2, the second derivative was also positive. Why do we care about that? Because that tells us the shape of our original function f of x. Let's think about this. My second derivative is positive, means I have to be concave up or a smiley face. First derivative negative means I have to be decreasing smiley face. So which half of a smiley face is decreasing? That would be the left half of a smiley face. Let's look at the next interval. My second derivative is negative, which means I have to be a frown. My first derivative is negative, so that means I have to be decreasing. So which half of a frown is decreasing? It's the right half of a frown. Looking at the next interval, my second derivative is positive, which means I'm a smiley face, concave up. My second derivative is negative, so that means I have to be decreasing. So which half of a smiley face is decreasing? It's the left half of a smiley face. Then we look at our last interval here. Last interval here, my second derivative is positive, so concave up or a smiley face. My first derivative is positive, so I have to be increasing. So which half of a smiley face is increasing? It's the right half of a smiley face. So what do? I just have to make the shape of the graph, go through those points, and be the shape in those given points. So I have to go to the point 0, 5, and before that I have to be the left half of a smiley face, so I do that. Between the point 0, 5 and the point 2, negative 17, I think that's what that is, 2 whatever it is, I labeled it pretty sloppy, I think it's negative 11 actually. I have to be the right half of a frown, so I connect those 2 points, making a right half of a frown. Now I need to connect the points 2, negative 17, and the point 3, or sorry, negative 11, and the point 3, negative 22 with the left half of a frown, so I connect those points with that shape. And then anywhere to the right of the point 3, negative 22, I have to be the right shape of a the right shape of a smiley, so I make it that shape. I put on my arrows on the end. I now have the exact proper shape of the graph without using any technology whatsoever. I have every important point other than the x-intercepts. There are 2 x-intercepts. I do not know what those x-intercepts are. They are not nice numbers, and I do not care in this class what they are. Yes, in college algebra, there are ways that you could have found them, but in this class, I do not care what they are. You did not need to label the x-intercepts. The only points that I expected were the y-intercept, the inflection points, which one of them was a y-intercept, and the minimum. So this is what I would have needed to see for full credit on the test. I would have needed to see a full analyzation of this entire thing, every single step broken out, every single thing done. I would have needed to see the 2 number lines on there, the test points on each one of those intervals, and the conclusions that you've made. So I need to see this work for you to get full credit on the test.